Okay, this morning we're going to talk about another very fundamental and important data structure in computer science, trees. The cool thing about trees is that they're so logarithmic. This is like a really, really bad pun, and you pretty much have to be reading the slides to understand it. But it's like real bad. Also, all the slides are on your dashboard, by the way, so if you're having trouble reading the really bad puns, you can just look at it there. So what is a tree? Well, ultimately, a tree is just a bunch of nodes and edges. So a node is this little circle thing, an edge is this little pointer to the next little circle thing. So it's very similar to a linked list where we have nodes and next item pointers. And it's also very similar to graphs and graph theory where nodes are instead called vertices and edges are still called edges. But an important thing about trees is that there cannot be any cycle. So a cycle means a tree cannot point to itself, or it can't be able to follow any kind of path that will eventually lead back to itself. So here are some trees. This is a tree. It's also a linked list, kind of. It's just a node with an edge and then another node. This is a tree. So this is the root node. We'll talk about some tree definitions in a bit, but the root node is the topmost item in a tree. And this root node has two children, and the left child has a right child of its own. And then this little single node is also a tree. What about stuff that's not trees? Well, this is not a tree because it's just a node, but it has a cycle. It points back to itself. This is not a tree because this node is pointed to by two other nodes. So each node can only have one parent for it to be a tree. And this is not a tree, this is actually two separate trees. So individually they're trees, but combined they are not. So let's talk about some definitions. The root of a tree is the topmost node. That's kind of obvious, it makes sense. If you think of a tree as actually the roots of a tree, then the root is the tree, and then the roots are the nodes, and so let's forget that analogy entirely. That doesn't really help at all. The parent is the converse of a child. So if a node has a child, then that child's parent is the same node. So parent and child are opposites. That's fairly straightforward. Descendant is any node that's reachable from a parent. So if you can take a node and then follow down the children path until you find this other node, then that other node is the descendant node. Ancestor is any node reachable from child to parent. So if you go the opposite direction from child to a parent node, then that parent node can be called an ancestor. A leaf/external node is any node with no children. So they're usually called leaves, the nodes at the very bottom of a tree that have no children of their own. An internal node is a node with at least one child, so it's the opposite of a leaf. So you're either a leaf or you're an internal node. All right, few more. The height of a tree, so these are fairly important to know and remember because very often interview questions involving binary search trees and trees will make use of these definitions as part of the prompt. So the height of a tree is the number of edges on the longest downward path from root to leaf. So basically, to find the height of a tree, you just see which leaf is the furthest most from the root, and then you count the number of edges you follow to get there. So we'll see some examples in the next slide. The height of a node is very similar as the height of a tree, except for it's the number of edges from a specific node instead of from the root node. So if you're asked to find the height of some random internal node, you just follow the same definition. You find the lowest leaf to that internal node, and you count how many edges down it is. The level of a tree is very similar to the height, so this can get kind of confusing. Normally people will ask height and will not ask level, but the level is the number of edges between the node and the root plus 1. So we'll talk about levels a bit in the next slide. And the depth is the number of edges between the node and the root. So the depth you count from the internal node up to the root, whereas with the height of a node, you count from that internal node down to its most distant child, most distant descendant, I mean. So finally, size is the number of nodes in a tree. So that's a pretty easiest and obvious definition. So any questions about any of those definitions? These two are sort of kind of the most important ones, plus size on this slide. But definitely you should be able to calculate the height of a tree. So the height of a node, oh, now I've done it. Now I've done it. The height of a node is the distance from a node down to its most distant child. So right here. Number of edges on the longest downward path from node to leaf. Whereas the depth of a node is between the node and the root. So depth you count up, height of a node you count down. All right, so a binary tree, yes, yes. This is such a mistake.
So the only difference between height and level and depth is just the 1 plus?
Yes, that's true.
What is the point of that?
To confuse all of us when we're talking about technical terms, and especially in interviews. We'll see. So, for example, with this tree here, this is level 1, this is level 2, this is level 3, this is level 4, so that kind of makes sense. Whereas the depth, this has a depth of 1 to the root, and this has a depth of 2 to the root. Yeah? Yes, a tree is a data structure, and it's a very fundamental and important one. It shows up in a lot of things in programming and in computer science. So a binary tree is a tree in which each node has at most 2 children. So it either has 0, 1, or 2 children. There are all sorts of different kind of trees. There's trees that can have 10 children. There's tries. There's all these different data structures. We're going to talk about binary trees mostly. And so binary tree at most 2 children. So this tree here is size 9. It has 9 total nodes. And it's height 3, because if we start at the root node and count the edges down to the lowest child node, the most distant leaf, we count 3 edges. Yes, Ignat. Oh, so Ignat was asking, what is the significance of numbers? We'll talk about that when we talk about binary search trees in a bit. So this is just definitions of trees, and then later on we'll talk more specifically about binary search trees, which is a special subcase of the family of trees. So this is a complete tree. That means every level, except for possibly the last, is completely filled, and the nodes are as far left as possible. So this definition will become more important when we talk about heaps later, but just know that a complete tree means that every internal node has 2 children, and every leaf basically is as far left as possible. So this level is full, this level is full, this level is full. This level is not full, but the nodes are as far left as possible. So this is a complete tree. Okay. So what about a balanced tree? So balanced trees are trees at which all leaves are at the minimum possible depth. That means this tree over here is not balanced because this leaf could be at, say, right here or right here, right? It could be at a level higher. But this tree is balanced because these nodes here have nowhere to go. They can't be in any higher level. So those leaves are at the minimum possible depth. So keeping trees balanced in general is really helpful for performance, and we'll talk about that also in a bit. But having a balanced tree is a great property to ensure that your tree stays very performant, fast access, insertion, deletion. Okay, so now let's talk about binary search trees. Yes, Dan?
So is a complete tree a balanced tree?
Oh, okay, so the question is a complete tree a balanced tree? And the answer is yes. Complete trees, by definition, are also balanced. That's a good question. Okay, so let's talk about binary search trees. Binary search trees are sorted. So they're a sorted data structure. So unlike hash tables, which we've used, which were unsorted, binary search trees are sorted. We did talk about linked lists. Those are sorted data structures. But binary search trees are basically a way to do very similar things as linked lists with much better performance. So for every node in a binary search tree, the left children are smaller and the right children are larger. So here the root node is 6. The left child here is 3, which is smaller, and the right child is 9, which is larger. And there are no duplicate keys allowed, basically, because then the sorting property would kind of fall apart and things would get messy. So if we look at each of these nodes, 3, the left child is smaller, it has no right child, that's okay. Binary search trees do not have to be balanced. So there doesn't need to be a child here. 0 is less than 1, but 2 is greater. So we can imagine that because each node maintains a sorted order, there's probably a way we can traverse the tree and return all the nodes in their sorted order so that we can use them. And in fact, when doing insertion, deletion, we'll make use of the fact that the tree is in a sorted order to radically increase our performance for those functions. Yes? Okay, so the question was, if the keys are strings instead of numbers, would we go by alphabetical order or would we use some kind of hash? And the answer is we would go by alphabetical order. You can actually sort your binary search tree however you like if you're implementing, like writing the implementation of it, as long as it's consistent so that 1 is always less than 3 and A always comes before C. Yeah. So why would you ever use a binary search tree over something like a linked list? What is the motivation here? Well, you get fast insertion, search, and deletion, especially when it's balanced. We'll see why in a bit, and then we'll talk about the runtime complexity of binary search trees. You get to sort as you go instead of all at once. So as you're inserting items into the binary search tree, you do so one at a time. And the tree must maintain its sorted order. So every time you insert, you're inserting it in the correct place to maintain the sorted order, which means that instead of having a huge mass of data and then having to run a sorting algorithm to sort it, and it takes a ton of time, this data structure is sorted as you insert items. So you pay a small cost when you insert to maintain the sorting order, but that means later when you want to read it back sorted, it's already done. You don't have to run a sort algorithm on 4 billion items because your binary search tree of 4 billion items is already sorted once you create it. So the implementation is fairly simple and it offers very good performance. So there might be situations in which you want to write a custom binary search tree instead of using a built-in data structure. And it's very easy to write one. It's basically small code complexity for good performance benefit. Some more reasons. It only allocates memory as needed. So when we made hash tables, maybe you started with 8 buckets and maybe it has to grow, but maybe at any given point in time, only half of those buckets are full. The empty buckets are still occupying space in memory. So hash tables probably use, in general, much more memory than actually necessary to store all the items. That's part of the performance memory size trade-off that you get with hash tables. Binary search trees don't have that problem. For every node you insert, you allocate one small chunk of memory for that node, but you don't have to pre-allocate all this extra space with binary search trees. And similarly, it doesn't have to reallocate memory to grow. So hash tables, once they reach a certain size where you can't really add anything more without terrible performance implications, you basically have to grow your hash table, which means reallocating a bunch of memory, copying everything over, and taking a pretty big performance hit to do those operations. Binary search trees do not have to do that at all. Okay, so let's talk about what log n means in terms of when discussing big O notation. So when discussing the complexity of computational algorithms, log n actually means log base 2 of n. So anytime log n shows up in computing, in computer science specifically, it actually means log base 2 of n. That might not be super intuitive, because actually when you talk about log of n in general math, if you don't specify the subscript here, you're generally talking about log base 10 of n. So we use a decimal number system. So in general math, log of n is assumed to be a decimal logarithm, like log base 10. In computing, log of n is assumed to be base 2, because computers are binary number systems. They're base 2. All right, so what is a binary logarithm? Here's an example. This is basically actually just the definition of logarithm. The log base 2 of n is equal to some number x. That's the same as saying 2 to some number x is equal to n. So that's how you can deconstruct the logarithm and think about it. You can also think about this definition here, which is in English, which is log base n is the power by which 2 must be raised by to obtain n. So here's some examples. Log base 2 of 16 is 4. That's because 2 to the 4 is 16. Log base 2 of 32 is 5. That's because 2 to the 5 is 32. Log base 2 of 143 is 7.15987 because 2 to the 7.15987 is 143. So any questions on the definition of logarithm? Yeah, Ignat. Right, so this is an important observation. Logarithmic numbers and logarithmic performance is not as fast growing as linear. So in terms of big O performance, constant time is the best you can ever hope for, but the second best is log n time. And then after that is linear n time. So log of n time is like the second best performance you can ever hope for from algorithms and functions. So if we look at these numbers here, linear amount of time on 143 is 143. A constant amount of time on 143 is something like 1. It's always the same. But the binary logarithm amount of time on something like 143 is 7 and some decimal numbers. So 7 is much, much smaller than 143. And we'll look at this a little bit more later also. All right, so let's talk about how would we search through a binary search tree. How can we, given we have a tree already constructed and we want to find a certain node in there, how do we do it with best performance? Well, we use the fact that the tree is already sorted. And we use something called binary search. So in general, whenever you have something sorted, it's fastest to search through it using binary search instead of linear search. So even in the case where we have, say, an array of sorted numbers, 1 through 10, let's make it bigger, 1 through 1,000. So we have a sorted array, 1 through 1,000. If we want to find number 254, or whatever item is at index 250, If we want to find node number 254 in this array from 1 to 1,000, what we can do is, instead of searching, starting at the beginning, and then just searching through every one until we find 243, that's a linear search. Instead, why don't we just jump into the middle of the array, see, oh, this is number 500. It must be less. So then we take half of those two arrays. We throw away numbers 500 to 1,000 because we know it can't lie in that range. So it's no longer useful to us. So we throw it away. And we say, all right, well, why don't we take half of the remaining array? So that's between 1 and 500. That would be 250. And we search there. So then we can throw away everything greater than 250. So in general, when using a binary search, every time you do one more increment of the search, you throw away half of the remaining data, which means it's very fast to search through because you don't have to look at most of the data. So let's talk about specifically how to do search on a binary search tree. In general, there's two ways you can do most iterative functions. There's the iterative way and the recursive way. Who here is familiar with the concept of recursion? Raise your hand. Okay, many people. Who here understands the difference between iteration and recursion? Okay, kind of less. So both are ways to accomplish the same thing. Both are ways to run some piece of code many times. Iteration basically is what you're used to, for loops, while loops. They just run until they meet some condition and then they end. Recursion is a little bit different. Recursion works by calling itself until it reaches some base case, some point where it should no longer run, after which it returns. So this is a recursive binary search. So the thing that makes it recursive is the fact that this function is called findRecursive, and then here we call findRecursive. So we call the method from within itself. So what would happen if you created a method called, for example, foo, and inside of foo, you call foo, and that's all it is. So it'd be like def foo, and then inside of foo, you call foo. What would happen? Stack overflow, right. Why would that create a stack overflow? Right. So if we have some function foo, and inside of foo, all it does is call foo, it's just going to constantly call foo forever until the actual stack that is in charge of what code to execute, so like the actual piece of hardware, will run out of memory, at which case that will crash the program. That's called a stack overflow. So every time you're on Stack Overflow, you're actually using a website named after this kind of crash that can happen in a computer. That condition is called infinite recursion. So it's the same as an infinite loop. If you have a loop that says while true, and you don't break out of the loop at any point in there, that's an infinite loop. That's going to run forever. Infinite recursion is a situation in which you call your own method from within yourself, and you don't have a way to return out and basically stop execution. So you have to be very careful when using recursion to ensure that in all cases the code will actually stop running. But recursion is often a very simple and elegant way to accomplish sort of difficult tasks easily. So let's look at this recursive binary search. So it's called findRecursive, and it has two input parameters. The first one is the key that we're looking for. So if we had one of those binary search trees with the numbers in it, and number 6 was one of the nodes, then the key that we're looking for would be 6. And node is sort of the placeholder for the node that we're currently looking at in the tree as we're searching. So what we first do is we check if the node is none or if the node is the key we're looking for. So if we've reached a point where we passed it an empty node, we pass none into this function, at that point there's nothing we can do. We can't really operate on none, so we may as well just return and stop execution there. If we pass in the node that has the key we're looking for, then our search is successful. We found what we were looking for. And at that point, we can return node because that was the node we were looking for. So this statement up here at the top is called the base case. This is the logic that's in charge of stopping the recursion from happening. So this base case here prevents infinite recursion, prevents stack overflows. All right, well, if we get past this if block, if we get past this condition, that means we have a node, but we haven't yet found the key that we're looking for. So what can we do? Well, we know that this binary search tree is sorted. Remember that the left child is always less than our current node, and the right child is always greater than our current node. So what we can do is we can compare the key that we're looking for with the key of the current node. So if we're on some node and it has the value 10, we're looking for the node with the value 6. We know 10 is not 6, so we know that we must go down the left side of the tree. We must go down to the left child because we know that 6 is less than 10. Does that make sense? So as part of that process, we get to throw away half of the tree and never even have to look at it. So, for example, node.key is 10, key we're looking for is 6, so we return the value that is the result of calling findRecursive. So we call the same method again. We pass the same exact key, but now we call the same method on the left child of the current node. So does that make sense to everyone? Do you understand how every single time we call find recursive, we're calling it on another node, but we're calling the same exact function just with a different parameter every time for node to accomplish finding what we're looking for? Okay, so this is a good question. What if we have a tree with some that's outrageously big? I don't know, 10 trillion items. And for every time we call find recursive, we actually need a tiny little bit of memory on the stack in the processor because it has to keep track of the full history of calls. So what happens if we Stack Overflow and hit the limit? Well, the answer is you crash. And there's not really anything you can do about that, but because of the power of logarithms, as we shall see in a bit, you would have to have a tree so large for that to ever be an issue that probably that tree can't fit in memory anyway. Okay. So what happens if we're looking for node value 6 and we're currently on 10? That was the example we just talked about. Well, 6 is less than 10, so we'd call the same find recursive on the left child of 10. Let's say the left child of 10 is a node with the value 5. Well, so now we're back to the top again. Key is 10. Node is just a node, but it has the value of 5. So is node none? No. Is node.key equal to 10? So node.key is 5. We're looking for 10. Sorry. Node.key is 5. We're looking for 6. We've been looking for 6 this whole time. Well, that's not true, so we don't do anything there. Is the value 6 less than 5? No, it's not, so we don't do any of this. So we do the final function call down here. So we call find recursive again with the right child this time of the node. So we know that we're looking for 6, the current value is 5, so we know it must be on the right subtree because we're looking for something greater than 5, and all the right children have a value greater than 5. So now let's say the right child is the one we're looking for. It is 6. So the value of key is 6. The value of node is just a node, but the value of node.key is 6. So we see that node.key is equal to key, so we can return the node. We're done. We found it. Any questions about this? Yeah, Ignat. Right. So what happens when we return the node? Well, we return node there, but then it actually pops back up to the function call that called find recursive, which was another find recursive. So we return node here, and then this is evaluated, and the value of this is now node because we just returned it here. So then this returns node, and then it pops again. We go up the stack, and then before that, we ended up calling this. So this returns node. So basically, once you hit the base case, you just get, like, the stack is unwound. It's called unwinding. And you just have a bunch of things that just basically return the value that you were looking for. Yes, Ignat.
Why would we use recursive over iterative?
So the question was, why would we use a recursive function over an iterative function? In general, you can do it both ways. For some problems, not really this one, but some are much easier to do recursively. And it's actually often much easier to reason about recursively. Instead of having to think about everything in one function, like what do I do when I hit a leaf? What do I do when I do this, when I have one child, when I have two children? When you do it recursively, all you have to think about is what do I do for these two parameters, not the whole tree. So all I know is what the key I'm looking for and what the current node is. So I can reason about the entire thing only using those two pieces of data instead of having to think about the entire tree as it exists. So recursive methods are often more elegant. Yes, Mohammed.
There are also some primitives recursive that cannot be done using
Oh, okay. So he said that there are some primitive recursive things So this is probably more computer science theory, but there's probably a class of problems that are not actually solvable using iterative methods that you have to use recursion. Okay. So how do you insert something into the binary search tree? Well, you actually use this exact search function, and then once you find a node without a child on the next side you're going to traverse, you just add it there. So you just search and search and search for the one that you're actually trying to add. Then you'll reach a point where you don't find it because it's not in there yet. But at the point where the node doesn't have a child and you can no longer traverse, you can just add it there. Does that make sense? Yes, again. Right. So it's actually not, it's going to be a slight modification of search where you have to keep track of the previous node also. Okay. So what about deleting a node out of a tree? Well, there's 3 different cases that you have to account for. The first is that the node has no children. The second is that the node has 1 child. And the third is that the node has 2 children. So let's talk about the case where the node has no children. So let's say we're trying to delete this pink node here. It's a leaf, it has no children. Well, it's as simple as just finding this pointer that points to it, making it point to none, and then the node is deleted. Nothing points to it, the garbage collector will eventually take care of it for us. Okay, so this one is pretty straightforward. What about the case where the node has 1 child? So in this case, we're going to delete this pink one. Well, we find it. Instead of making the parent pointer point to none, all we have to do is swap the child position. So we put the child where the original node was, and then we've deleted that one, the one with 1 child, the pink one. What about the case where there are 2 children? Well, let's say we're trying to delete the root node of this tree. In this case, it's a little bit more complicated than the other 2 cases. So we have to find what's called the in-order predecessor. So what we have to do is we have to go 1 step left and then find the rightmost node from there. That node we will swap up into the position of the deleted node, and then you take whatever children that node had and put it where it was before. So I'll say that once more. If we're deleting this root node, we have to go 1 step left and find the rightmost node. So follow down the tree right until we can't go right anymore. And then we swap that node we find into the position that we've deleted, and we take that node's children and put it, basically this is doing the same as the 1 child situation, so we just swap that in there. So why does this work? Well, let's think of an example in which this root node has the value 10. And then let's say this node we're trying to delete has the value 4. Does that work? Let me think. Yes. Kind of, not really. All right, let's say this blue node is 7. So the node we put in the place of the node we're deleting has to be greater than all the left children, but smaller than all the right children. So how do we guarantee that? Well, by finding the rightmost node in the left subtree, that node will always satisfy the condition where this node must be greater than all these other nodes in the left subtree, but it will be less than all the nodes in the right subtree. That's because all the nodes in the right subtree must be greater than this node, which means that they're also greater than this node by definition, because this node must be less than this node. And all of these nodes here, these are all less than this node, and they're also all less than this node, because this node by definition is greater than this node, and these are also all less than this node. So we can reason that the rightmost node in the left subtree must be greater than all of these nodes and less than all of these nodes and these nodes, which means it is the one singular node that we can put in the place of the one we deleted. So that might be a little bit obtuse. So what we'll do after this lecture, I'll go over to the whiteboard, and if you're confused, we'll draw out some example ones, and we'll delete them, and we'll follow the algorithm to see how it works. Yeah, Ignat. Oh, so Ignat is saying, what about the situation where we have this node here that we're trying to delete, and it has two nodes as children? What do we do? Well, we do the same thing. We find the rightmost node in the left subtree, which in this case is this one, and we swap it in there. Because this one is always going to be less than this one, so having this one as the parent of this one satisfies the condition. Okay. Well, this one will stay there, and this one will take that place if we were to delete this one. Okay, so for every node in the binary search tree, the left child is always less than, and the right child is always greater than the value of this node. So if we were to delete this node, we could swap in this left node, put it here, and it's still going to be less than this node, which will satisfy the binary search tree property. Okay, so let's talk about the big O runtime of binary search trees. So what is the average case for the amount of space that a node will take up? Oh, sorry, a binary search tree will take up. So for n items, how many units of memory do we need? N, right. So for every item we add, we create a node, and we store it. So we have one node per item in the tree. What about in the worst case? Well, actually, let's sort of define what the worst case is. So given a binary search tree, what is the worst case? Well, the worst case would be if our binary search tree actually was just a big, long line of nodes that only had one child. So if our tree, the root node, has value 12, then it has a child with value 10, and that has a child with value 7, and that has a child with value 5, but none of those have any other children. Suddenly, our binary search tree is actually just a linked list, because everything only has one child, so now it's a linked list. So the worst case in space is still O of n, because there's still only one node per element in the tree. What about searching? So what is the average case to search for an item in the binary search tree? Yeah, Ignat. Log n, right. Why is it log n? Right. Every time we make an iteration in our search algorithm, we're throwing away half of the data, half of the tree. We don't have to search through it anymore. So log base 2 of n indicates that we're having the amount of data that we have to look through every time, and it has really good performance implications, as we'll see. What about in the worst case? So remember, the worst case binary search tree is actually just a linked list. Every node only has one child. So what's the worst case search through that? Yeah, Mike? Linear time, right.
Actually, it's sorted, right?
It is sorted, but the only way, yeah, we can't jump. It's not an array. We can't just index into it. So we still have to search through to find the item we're looking for. So the worst case search is linear time. What about average case for insert? Right, because all we're doing for insert is a search plus a constant amount of time to just set up some pointers to add the extra item. So log n for insert. Worst case, the exact same as search. It's a it's a linked list. We have to search through the whole thing to find the last element, and then we add it on the end. That takes linear time. Delete, same as everything else. Log n, we have to just search and then swap some pointers. And worst case, linear time, we have to search through the whole thing to find it, and then swap some pointers. All right, so why is log n good performance? Let's imagine a binary search tree with 2 to the 32 items in it. Well, 2 to the 32 is this number here. It's 4,294,967,296. So that's a really big number. This is a big binary search tree. There's a ton of stuff in it. So what is the worst amount of time? Like, what is the maximum amount of nodes that we'll have to visit to find our item. Let's consider our item is a leaf. It's at the very bottom of our tree. What is the maximum amount of nodes? Yeah, David. The height of the tree. Right. So what is the height of our tree? Yeah, so the height of the tree is log base 2 of this number. So it's 32. So at most, we only have to touch a maximum of 32 nodes to find the node we're looking for out of a tree of 4 billion items. So that's crazy performance. If this were a linked list with that many items, we would at worst have to touch every item, 4 billion. If this were a hash table and we could do it in constant time, maybe we could do it in one operation, one sort of theoretical operation. But at worst, with a binary search tree, we only have to do 32 theoretical operations. So the order of performance, like this number grows so slowly compared to the speed at which the number of items grows, that log base n, for most intents and purposes, is like the same performance as constant time. Only when you're working with theoretical, like 10 trillion items, does logarithmic complexity start to actually become much worse than constant time complexity. Yeah?
Does this apply on any binary, or does it have to be a tree?
That's a good question. Does this apply to any binary search? And the answer is yes. As long as the stuff you're searching through is sorted, this applies to any binary search that you can do it in log n time. And so it's just like outrageous good performance. So what does this mean? Actually, this means that many hash tables, not in Python, but many other languages, implement hash tables and sets as binary search trees. So the theoretical performance is not as good because instead of doing insert and retrieve in constant time, you do it in log base n time. But because the memory performance is better, you only allocate a tiny bit, you don't have to allocate any extra. In most real world data sets, they found that binary search trees are actually more performant than hash tables. Also, just for fun, let's think about the situation. So most of you have probably made a hash table by now, and you probably used linked lists, one of your own making, for collision resolution. Instead of using linked lists for collision resolution, why not have a binary search tree? So you could have an array of binary search trees, and then instead of inserting something in n time at the end, or retrieving it in n time, you can retrieve it in log n time. So that would overall actually improve the performance of your hash table. So in many situations, in places where you could use a linked list, you could actually use a binary search tree to do the same thing, but with better performance. Okay, that's it. So any questions about binary search trees? Yeah, Ignat. In a linked list, you can have duplicate keys, although you'll only return the first item you see. So it's not actually, doesn't really work that much if you're doing like key value mapping with a linked list. Because if you put two different values for the same key in there, when you retrieve it, you have no idea which of the two values you're going to get out.